Welcome to Microlecture 7, Identifying Resonance Patterns. It's important to be able to look at a molecule and know if resonance is possible. Here are some very common structural motifs that you can learn to recognize and know that resonance is possible here. Okay, so here's these motifs that you might recognize. There could be an allylic lone pair. That means one position away from a double bond, allylic. And if I follow those curved arrows, then the resonance structure that we would get places a negative charge on the carbon atom there. Two lone pairs on the carbonyl oxygen. And so those two are resonance pairs of each other. Another motif that you might notice is the positive charge sitting one away from a double bond. So that's an allylic carbocation, and the electrons are delocalized across those three carbon atoms. So the double bond in the resonance form is moved over one, and the positive charge, don't forget, is now on the carbon that we removed electron density from. So these two are resonance structures of one another. And you could also have a carbocation one away from a lone pair. So this happens and is a red flag for the opportunity to make a resonance form. And so we're going to create a pi bond between this carbon and oxygen. And when we do that, this oxygen now bears a positive one formal charge. These last two are just good for noticing if there's an opportunity for resonance. This one is just a carbonyl, and isolated carbonyls we wouldn't actually draw this resonance form for, because the resonance form is a very minor contributor. So we could put three lone pairs on the oxygen, giving it a negative charge, and simultaneously pull electron density away from the carbon atom, giving it a positive charge. You see, this is a lot of charge separation, and so we'll talk in the next video about the fact that that's not really ideal and is representing a less likely picture of the molecule. On the other hand, carbonyls are still a red flag for the opportunity to do resonance. So sometimes this carbon-oxygen bond is part of a larger structure that involves more likely electron delocalization. So it's good to know that one. And then the last one is just, the opportunity for multiple bonds in conjugation with one another. So that means alternating double bond, single bond, double bond, single bond, whether it be in a benzene ring like this, so a closed ring system, or even in a linear system, where I'll doodle on the bottom here. You've got conjugation like this, and sometimes that culminates in some sort of a functional group. So I'll just put a carbonyl or something like that there. This is a cross between the last two examples here of motifs in which you would see electron delocalization. And so the more conjugation you have in a molecule like this, the more alternating double bonds and single bonds you have, the more likely it is that there are some strong resonance contributors that we can draw to demonstrate the electron delocalization. So the drawing here, if I follow all the curved arrows, just moves the double bonds into three different locations on the ring from what they were originally. So, these are two different ways to depict a benzene ring. Okay, so let's practice drawing resonance forms for each of the following. This time you're not given curved arrows and partial structures of possible resonance forms, so you've truly got to come up with it on your own now. Pause the video, see how much you can come up with, and then come back to it. The second structure here has multiple resonance forms. The other three have just one. And so if I wanted to draw a resonance form of this compound, it's a cyclic structure, I would push the pi electrons over into this carbon-carbon bond that is electron deficient. It's got a carbocation sitting there. So we generate a new 5-member ring here with a double bond sort of relocated and a positive 1 formal charge sitting on the carbon that we took electron density away from. And that's it there. The second structure, we have some lone pairs on oxygen missing. Let's draw those in. One of those lone pairs is used to create a carbon-oxygen double bond. And then once you make a bond to this carbon in the ring, you have to break a bond from it because otherwise you're violating the octet rule and creating a hypervalent carbon atom. We can't have that. So the resonance structure here, I'm going to redraw the 6-membered ring, and I'm going to draw those double bonds that had nothing to do with the resonance or electron delocalization that was happening. I'm going to draw the formal 1- charge and lone pair that's sitting on the carbon atom. And I'm going to draw in a carbon-oxygen double bond that was created, leaving 2 lone pairs on the oxygen. And again, the connectivity hasn't changed, the net charge hasn't changed, it's still -1. All that we're doing here is moving around pi electrons. We can do that again because of the conjugation in the ring system. So the negatively charged carbon is an electron source. I can move those electrons in to make a carbon-carbon double bond, and then break the existing carbon-carbon pi bond and kick those electrons off onto carbon atom. So we've got a new 6-membered ring, negative charge on this carbon, and a double bond here for our resonance contributor. One more time, we can move these electrons into the bond to create this pi bond, make a bond, break a bond, and give the electrons to this carbon atom, creating a 4th resonance form. Okay, and so that would be it, because if we push the electrons around one more time, we would go back to the original structure. So these are resonance forms of each other, and that I believe we've gotten all of them. The next problem is an allylic aldehyde. So we can use the pi electrons in the carbon-carbon double bond and kick them off onto the electronegative oxygen atom to show another way that this molecule can be drawn, although this would be a less important, if you will, resonance form. So next video we'll talk about major and minor resonance forms. This resonance form is introducing a lot of charge separation. So a +1 charge on this carbon that we took electron density away from, negative charge on the oxygen. That's not as energetically stable as overall neutral. So the previous drawing is a more accurate representation of this molecule. If that is troublesome for you, You can go in and label hydrogen atoms wherever they are, just for clarity, and there's no problem with that. It's not breaking any rules. So I recommend that you do that when you're generating, carbocations especially. They tend to be confusing initially for students taking organic chemistry. So just know that hydrogen is still, sitting there, and so a carbon atom, let me draw my structure, and so a carbon atom with 3 bonds and no lone pairs indeed has a positive 1 formal charge. So just remind yourself that you know how to calculate formal charges, and so that's all we're doing here when we're labeling formal charges on these atoms. Okay, so this last one, we've got a carbocation, and it's adjacent to an atom, a heteroatom. So the nitrogen heteroatoms are non-carbon, non-hydrogen atoms. Has lone pairs. So we can kick the lone pairs into the carbon-nitrogen bond and make a pi bond that then satisfies the octet of that carbon and satisfies its valence, so it no longer has a formal charge. So I'm just going to fix this nitrogen real quick. It should have another bond to it. That should be there. Let's just put a methyl group there. And then we'll go ahead and draw that in here as well. We used the lone pair to make this double bond, and then we've got the carbon that is now happy neutral carbon atom, and the nitrogen now has 4 bonds and no lone pairs, and so it bears a positive 1 charge.